Hey guys, welcome back. We are going to do the chapter 12 examples in this video. And we have a few problems to do, and let's just dive right on in. So the first one, which is, just so we know how this works, this is chapter 12, problem 12 in the Burge 5th edition. All right, so this is chapter 12, problem 12. All right, the next one, chapter number 2 here, is chapter 12, problem 15. Okay, so those are the problems I'm getting from the book. That's where they're coming from. All right, so these are from your book, and let's talk about it. The vapor pressure of phosphorus trichloride is 119.7 millimeters mercury at 25 degrees Celsius. Perfect. There's your question word. What will the vapor pressure be at 70 degrees Celsius? All right, it gives you molar heat of vaporization right here. All right, it gives you a vapor pressure at 25, oh, it jumped on me, sorry about that, 25 degrees Celsius. All right, so what equation will we use? Well, we got vapor pressure and we got delta HV, so that's probably going to be the Clausius-Clapeyron equation. So we're going to have natural log P1 over P2, right, and that's in the parentheses, is equal to delta HV over R times 1 over T2 minus 1 over T1. That's how we derived it, all right, or it was derived for our book. There's different ways you can do it with negative delta H and T1 minus T2 and all sorts of stuff, or P2 on top. Now, we're looking for vapor pressure, and so I like solving for the top vapor pressure. So I like solving for P1, which means 70 degrees Celsius has to be T1, right? Now we'll change that to Kelvin, of course. That means T2 is 25, and P2 is 119.7. So it doesn't matter which one in the problem is first, which pressure or temperature are first. We just need to know that these two go together and these two go together. That's what we need to know. And so it doesn't matter which one's P1 and T1 and P2 and T2. They just have to go together. And then finally we got delta HV is there, and we know what R is, right? R, of course, is the constant, right? R is 8.3145 joules per mole Kelvin. All right, well, let's plug these numbers in. All right. And so we have natural log P1 is what we're looking for. All over, we have, what is that, 119.7 millimeters of mercury equals, now I'm going to make this, it is 31.63, it's kilojoules, right? You see the K, kilojoules? We're just going to do a times 10 to the third and make that joules per mole, right? So I'm getting rid of the kilojoules. Why am I getting rid of the kilojoules? Well, because R here is 8.3145 joules per mole Kelvin. So now I have joules and joules, and we're good there. Times 1 over T2 minus 1 over T1. Now, our T's, we got to add 273, right? 0.15 here. So that's 298.2 for T2. And T1 is 70, right? So that's 70 plus 273, 70.015, right? So that's 343.2 with sig figs. So 343.2 Kelvin. All right, to do first, and again, this is in parentheses. All right, we got to do everything on the right-hand side. All right, and so if I do everything on the right-hand side, I know where my calculator is. If we do everything on the right-hand side, we should get 31.63 times 10 to the third divided by 8.3145 times 1 divided by 298 minus 1 divided by 343.2. I'm getting negative 1.673. And the units are gone. So we have natural log P1 over 119.7 millimeters of mercury. All right. What do we do now? Well, we got to raise both sides to E. Right? Because natural log and E, right, they cancel. And so then I would have P1 over 119.7 millimeters of mercury equals positive, it's now positive 0.1876. Then I have to times both sides by the 119. So for P1, I get 638 millimeters of mercury. All right. So to recap real quick, all right, we did this side first, got a number right here. And we had to take both sides to the power of E, and then these cancel. I have that number, and then we multiply by both sides by 119.7. So that's the first one.